Hi everyone. I decided to record this supplemental video to go over typical mistakes which some of you committed during test 1. The main problem turned out to be question 2. Even though we discussed these eigenvalues and eigenvectors so much, but nevertheless, many of you, not few, but many of you still had difficulty finding these eigenvalues and eigenvectors. So I decided to record this video to go over this problem again. My plan is to give you two examples, 2 by 2. The first one is for 2 by 2 matrix, and the second one is for 3 by 3. But this particular video will be different from the previous ones, which were tutorial 1, tutorial 2, tutorial 3, I think. It will be different in that, in that the main emphasis will be put on how to realize, how to detect your mistakes. So along the way, I'm going to go over this technique once again, but along the way, I'm gonna emphasize this idea to you. So let's start with 2 by 2 matrix. 2 by 2 matrix. So the example is question 1b. I don't remember, was it the second tutorial, the first tutorial? It doesn't matter actually, because I'm going to solve the same task twice. So this is the first task, first problem. So here you have matrix A. 4, 1 is the first row, and the second row is 3, 2, 3, 2. Okay, and the assignment is just like in your test 1, question 2. So your task is to find eigenvalues, then to find eigenvectors, then to build spectral and model matrices based on this outcome. So I think that a bit better, even though your task during test 1, question 2, was dealing with the 3 by 3 matrix, but I think it's a good idea to start with a smaller example, just to get the idea, not to get distracted by arithmetics, by very big transformations and so on. So, okay, let's start by calculating lambda. You know, to calculate lambda, you need to calculate determinant of this matrix, but the unknown lambdas should be subtracted from diagonal elements. So let's do it. So I abstracted lambda from diagonal elements, and now I set up this determinant equal to 0. I think the image maybe is not quite good. Okay, so let's try and calculate this. Determinant minus 3 is equal to 0. Now I need to do this multiplication. It's all pretty straightforward. Lambda squared minus 2 minus 4 will be minus 6 lambda. Here we have plus 8 minus 3 will be plus 5. So this is super easy quadratic equation. You can either use the well-known formula with discriminant and everything, but sometimes it's very easy to guess the factorization. I think that I will go for the second option because it's indeed very easy to guess this factorization. And moreover, what I like about this factorization, that it gives you an opportunity to check your roots. So if you try to do this multiplication again, you will have to end up having this equation, which is the sign, which is the indication that the roots are absolutely correct. So, okay, so the first root is 1, lambda 1 is 1, and the second root of this equation is 5. So we did find these eigenvalues, nothing fancy. But now it's time to recall how you needed to find eigenvectors. Let's divide the page into 2 columns. So I'm going to deal with first lambda here in the first column, and with lambda is equal to 5 in the right column. So how did we calculate eigenvectors corresponding to each of these lambdas? The thing was that you needed to look at this matrix once again, even put a yellow circle around it. And you need to substitute lambdas in this matrix with current value of number, which is 1. So 4 minus 1 will be 3. 3, 1 is the first row with this matrix. And then the second row will be 3. 2 minus 1 will be 1. So this will be the matrix. you need to multiply it by our vector e1, which has components, only two components, x1 and x2, and is equal to 0, 0, 0 vector. So this was our central equation, which allowed us to find this x1 and x2, which are components of our eigenvector corresponding to lambda is equal to 1. But usually people, once you've done this task many times, you get used to it, you become lazy, and that is why maybe it's better just to write down this matrix, that's it, without going into detail. Okay, so what is the indication that your matrix is correct, that your lambdas is correct? The indication is that you always have two rows in this matrix, and these rows should be proportional. And if they are not proportional, it's the sign that you made a mistake calculating lambda probably, or maybe you didn't manage to substitute them properly. Sometimes even these kind of stupid mistakes can happen, especially during exams when you're under time pressure. So, but in my case, everything's correct. So the rows should be either proportional or even maybe equal to each other. In this situation, I have the second row equal to the first row, which means that it's redundant. And that is why instead of the first row, I'm getting back to the equation. 3x1 plus x2 is equal to 0. Now we need to come up with two variables, non-zero variables, by the way, very important, which would satisfy this equation. Maybe it's better to write it maybe in this way, I don't know. It's just a matter of taste. And then our first eigenvector would be if you set x1 equal to 1, the second variable will be -3. So that's it. But now the question arises. As you said, as I mentioned before, the main emphasis of this tutorial is not to solve these equations, solve this task once again, because you can watch my previous tutorials. But the main emphasis is on the techniques of how to find your mistakes, how to do it quickly and effectively during exams and tests. So how can we check this vector, that this vector is correct? Maybe I made some careless mistakes, who knows? So to do this, I always do checking, actually. How can we check this? We need to recall definition of eigenvector. Let's write it down here. Let's waste some time on it, because it's super, super important, as you already realized after test 1. Okay, so what is the definition of eigenvector? Eigenvector, I don't know, E corresponding to eigenvalue lambda. I'm not writing every single word, I'm just saying them. Eigenvector E corresponding to given value of lambda is a non-zero vector, by the way, non-zero vector in the first place. I'm even highlighting this vector, which satisfies the following equation. A times this vector, A is our initial matrix, is equal to lambda, our current lambda, times this vector. So this gives the idea how you can check your result. How can you check that your vector E1 in our case is absolutely correct? You need to calculate the left-hand side of this equation, then compare to the right-hand side. And if the equality holds, it means that you're absolutely correct. So let's do it. It sounds like it's quite time consuming, but in reality it's not. If you practice this skill quite a few times before the test, before the exam, you will find out that it's actually super easy. It's worth spending time on it. So okay, let's start. So where's our matrix A? Our matrix A was given 4, 1, 3, 2, if I'm not mistaken. No, I'm not mistaken. Then our vector E1 is 1 minus 3. So this is my left-hand side. Now all I need to do this multiplication, which is super easy, of course, for you. I have no doubt about it. So the first row times this column. 4 minus 3 will be 1, okay? And the first row will give us the second component. 3 minus 6 will be minus 3 minus 6. I don't know. No, what I'm saying? Minus 3, of course, minus 3. And then, so this is our left-hand side. What about the right-hand side? The right-hand side should be lambda times our vector E. But our lambda is 1. Vector E is 1 minus 3. As you can see, they coincide with each other. So it means that at least our first vector is absolutely correct. So that's how you could have checked your result, by the way. Okay, so we immediately know that at least our first eigenvector and first eigenvalue are absolutely correct. Okay, let's do the same thing, apply the same reasoning to the second lambda. So lambda is equal to 5. How do we find the eigenvector corresponding to lambda is equal to 5? Again, we are getting back to this matrix and substitute lambda with 5 this time. So it will give us 4 minus 5 will be minus 1. So it's minus 1, 1. And the second row will be 3. 2 minus 5 will be minus 3. And I'm becoming a sort of lazy. I don't fancy writing this down again because all we need to do, we need to deal with this matrix already. Okay, so do you remember what is the sign that our lambda was correct? Our lambda is equal to 5 is correct. These two rows should be proportional, and they are proportional indeed, because the second row, as you can see, could be obtained from the first row by multiplying by minus 3. So it's absolutely correct. At the same time, it means that the second row is redundant, and we can get back to our equation presented by the first row. Oh, 0, 0, sorry, I make a mistake myself. X1 is equal to x2. So our second eigenvector would be 1, 1, just 1, 1. Again, and let's do our checking first. I never neglect doing checking, actually. Okay, so again, we need to take this equation. So A times E2 should be equal, I put a question mark here because I don't know yet, lambda 2 E2. Lambda 2, of course, is 5. Okay, let's do this multiplication. So our vector, oh no, our matrix A was 4, 1, 3, 2, and our current vector is 1, 1. Let's do this multiplication and see what happens. Okay, so 4 plus 1 will be 5. 3 plus 2 will be 5. So the left-hand side of this equation, of this definition actually, gives us a vector with components 5, 5. What about the right-hand side? So lambda 2 times E2. Our lambda 2 is equal to 5, and our vector is 1, 1. As you can see, we obtain the same result. It's a very good sign. It means that we can relax. Our eigenvectors and eigenvalues are absolutely correct. So this is the technique how you could have checked your result. Okay, and as for spectral metrics, just let's write them down. So spectral metrics and model metrics. Let's discuss them once again because it's very important. Okay, what is spectral metrics? Spectral metrics is a matrix whose diagonal elements are lambdas and the remaining elements are all zeros. So in our case, it's 2 by 2, of course. So the first lambda was 1, 1, 0, and the second lambda was 5. So that's how spectral matrix looks like in this case. What about model matrix? You probably remember the definition still that the columns of your model matrix should be eigenvectors, but they shouldn't be given in an arbitrary order. The order depends on which order you presented your lambdas here. So if the column, this column, corresponds to lambda is equal to 1, this is the first column. So the first column here should be only vector E1, corresponding to the same value, not vice versa. And the same goes for the second column. The second column symbolizes or represents lambda is equal to 5. That is why we need to put the second vector, which was 1, 1 here, not vice versa. You are not allowed to swap the order. It's super important. In linear algebra and order is super important because linear algebra deals with matrices, and order in matrices matters a lot, of course. Okay, but so yeah, now you found out one technique as to how to check your eigenvalues. But you know what? Another important technique is how to be able to detect your mistakes. So probably from the very beginning, maybe earlier. So let's pretend that I made a mistake. So let's pretend that instead of lambda 1, I got minus 1. I could have easily made this stupid mistake, of course, careless mistake. So how the situation would look like and how to spot it if you went so far, because all this checking of eigenvectors looks like quite a long story, of course. But is there a way to detect this mistake even earlier? Let's discuss it. So let's pretend then for my particular task, the same task, I made a careless mistake and I obtained lambda is equal to minus 1 instead of plus 1. What will happen? Of course, I need to follow the procedure again. I need to take this matrix, this yellow matrix, and substitute my lambda, my wrong lambda, but I'm still not aware of this. So 4 minus minus 1 will be 5, 1, 3, and I'll got here, 3 here. Okay, you can easily see that these rows are not proportional, and that is why you realize that you made a mistake. But what if you didn't know about this technique? What happens next? So let's pretend that you forgot about this wonderful technique, this one of checking these proportional rows, and you decided just to push on. You decided to solve this system and so on. Let's restore this vector here because it will be more convenient to discuss it. Okay, so you decided to solve this problem. How can it be solved? Of course, you know that we need to use Gaussian elimination. It's such a wonderful technique, even in the cases when matrices are very small. So what do we need first? I think it's a good idea to divide the whole second row by 3, because the fewer numbers, the better. And then it's a good idea to swap the first row with the second row, because the ideal situation when you have this one in the top left corner. Okay, so now we are ready. So what we are doing, we are rewriting the first row as it is, and we need to eliminate this guy. We need to get rid of it. We need to turn it into 0. To this end, it's a nice idea to multiply the whole first row by -5 and add the result to the second row. So you will see that we have -5 plus 5, we got our 0 here, -5 plus 1 will be -4. And again, it's better to reduce the numbers. And in this case, it's a nice idea to divide the whole second row by -4, because 1 definitely looks nicer than -4. Okay, and now you are not suspecting anything. You are absolutely sure that you are doing everything correct, that now you will get an eigenvector and you will get a right answer. You failed to detect this mistake from the very beginning. We are just modeling the situation when you forgot about this first technique. Now we are going to discuss the second one. Okay, what happens? So you follow, according to this Gaussian elimination method, you need to find this so-called, remember, leading elements. So this is the leading elements for the first row, and this is a leading element for the second row. Look at this, no free variables at all, no free variables at all. What does it mean? It means that you need to get back to your system of linear equations immediately. This is the second step of our Gaussian elimination. And you just need, so you don't have parameter t this time because there are no free variables. We usually denote free variables as parameter t, but no parameters t here. It means that maybe it's a good idea just to push on, to switch to the next step. And you know what we'll get. You will get that the second component is 0, and substituting this result to in the first equation, you will get the same result for the second. And you get this result. So my vector E is 0, 0. What's wrong about it? It contradicts the definition of eigenvector. All eigenvectors, do you remember, are non-zero factors in the first place. Do you remember I just wrote down this definition somewhere in the previous pages? And definition started with this phrase: eigenvector is a non-zero vector which satisfies the following equation. So in the first place, it should be non-zero. So that's how you could have detected this mistake. And some of you during test 1 did obtain this zero vector, and it was considered to be a big mistake, actually. So now you know. So to wind up, to make a review, so when you are dealing with this task of finding eigenvalues and eigenvectors of some matrix, you have at least like 2 techniques, maybe 2 tricks to detect your mistakes, your errors on the fly, because it's super important to be able to do it on the fly during the test and exam, because you are under time pressure. You don't have time to think too much and to spend too much time. So my first recommendation would be for you as following. So once you found lambdas, be skeptical about it. Maybe you already did a mistake. Sometimes you get so nervous, so hurried during a test that you're absolutely sure that your lambdas are correct, but in reality they are not. So just don't take it too hard. Just push on. You write down this matrix, this system of linear equations for which your intention is to find eigenvalues. And if you notice that these rows are not proportional, this is a perfect sign that something is wrong with your lambdas. Get back to your lambdas, check your how is it called, characteristic equation and so on. If they are correct, so maybe you just didn't substitute them correctly. This happens sometimes as well. So for example, if there was suppose 4 minus 1, which is 3, but you somehow you put 5 or maybe minus 3, these things could happen as well. But if everything is correct, then you can move on. Then you find the coordinates of this vector, and don't be lazy about checking these coordinates. You know, one of the many typical mistakes which some of you did during tests, they just swapped these two components. Instead of writing 1 minus 3, some of you wrote minus 3 1. This is especially frustrating. Of course, it's all due to nervousness, and I tried not to reduce the number of marks for this particular task, but you can agree that it's very, very frustrating. That is why it does make sense to do this checking by definition, that A, matrix A times your vector is equal to lambda times your vector. It does make sense to. And again, maybe you even missed this point. Maybe you were so nervous that you didn't care. You forgot about this technique about proportional rows. Once you get this strange result that your eigenvector is 0, just remember it's just a complete nonsense, because according to definition, eigenvectors should be non-zero in the first place. So I hope this task, this problem, this 2x2 example was quite inspiring to you. And now let's do the same thing for 3x3 matrix. 3x3 matrix, which is close, which is more similar to the one you got during your test. And so I chose question 1b from tutorial 3 this time, because it's super excellent example. We can discuss our techniques, which are the same actual techniques once again. And moreover, I'm gonna even discuss some more additional techniques when you deal with this Gaussian elimination. Okay, let's start. So in this question, you have matrix 3x3 this time. The first row is minus 1, 3, minus 1. The second row is minus 3, 5, minus 1. And the last row is, you can see properly here, minus 3, 3, 1. So this is our matrix. And the assignment is absolutely the same, just like in question 2 in your test. So you need to find eigenvalues, eigenvectors, spectral matrix, and model matrix. But this time it will be much longer, because 3x3 it's definitely a much longer and more complicated task. Okay, let's start doing nevertheless. So the first step is calculating lambdas, eigenvalues. To do this, we need to subtract lambdas from diagonal elements and calculate this determinant. So minus 1 minus lambda, 3 minus 1, this is my first row, correct? Yeah, correct. So minus 3, then 5 minus lambda, then minus 1, this is the second row. What about the third row? It will be minus 3, 3, and 1 minus lambda. Sorry for this mess, it's just nothing. Okay, we need to set it equal to 0, but I'm not going to write it. I'm going to calculate this determinant immediately. What is the best recommendation as to how, what is the most efficient way of calculating determinant? The usual recommendation is to use this expansion along the row or column. But the column should be the one which has at least 1 0. If you have zeros in your matrix, go for this row or column which contains at least 1 0. But if it contains even 2 0, it's even better, of course. In one of the variants during your test 1, there was such task actually. So some of you were quite lucky. It was either A, B, C, or D. You know that you had 4 variants. Okay, so in one of these variants was such a beautiful situation. But unluckily, we are not so lucky in this particular task. So maybe it doesn't make sense to look for some best row or column. Let's just go for the first row. I'm going to do the expansion of this determinant along the first row. So the first element is minus 1 minus lambda times what? We need to cross out the first row and the first column and calculate this determinant. I prefer to put it into brackets. 5 minus lambda times 1 minus lambda plus 3. Then we move along this first row. The second element is 3, but it should be minus 3 when you calculate determinants. You know about this. So this time we are crossing out the first row again, but the second column. So you can see this matrix. So it will be minus 3 times 1 minus lambda and minus 3, not plus 3. Minus 3, I insist. Okay, and the last element, the last element is minus 1. I was tempted to write plus 1, minus 1 times what? Again, we are crossing out the corresponding row and column, and we have minus 9, this by this, plus 3 times 5 minus lambda, parentheses and brackets are closing. And now comes the most annoying and difficult part. Of course, this is a cubic equation, and you already know the method of calculating, of solving cubic equations, but it's better not to apply this method. It's better not to do all the multiplication. It's better to apply a more wiser approach. It's better to try and factorize before it turns into a real cubic equation. So let's try and do it. And the recommendation is that you do need to do some multiplication, but not don't try to do the whole multiplication. So, for example, my first impulse is to get rid of these brackets, but not of these parentheses. So minus 1 minus lambda, this guy, gets multiplied by this guy. 5 minus lambda, 1 minus lambda. And again, this term times 3 will be plus 3 times minus 1 minus lambda. So you can see this term, this long term, looks quite ugly and big and scary. But you know what? It's better not to try and simplify and multiply it. It's better to leave it as it is. Let's simplify the rest. So what do we need? What do we have here? Inside of these brackets, we have minus 3. Minus 3 will be minus 6. And minus 3 times minus lambda will be plus 3 lambda. Okay. And finally, I think we can do the last, the remaining brackets. So minus 9 plus 15 inside brackets will be 6. But minus in front will give us minus 6. So this guy will give us minus 3, but it will be plus 3 lambda. Plus 3 lambda. Okay. So what next? What next? We need to, I think that we need to do the further multiplication, but don't touch this term. I think it's going to be crucial for our future factorization. Okay, I'm just rewriting this terrible first term, and I'm doing the rest of the multiplication. So it will be minus 3 lambda from here. The next term gives me plus 18. This times this minus 9 lambda, and I'm just rewriting these two guys. Plus 6 plus 3 lambda. So I'm going to switch to the next page because I'm running out of space. Okay, so what can we do here? Again, I'm going to rewrite this terrible term once again because I really like it. It will be helpful to leave it as it is. And now, as for remaining terms, we need to find so-called like terms. So what immediately can be seen that minus 3 lambda plus 3 lambda gets cancelled out, and we are left only with minus 9 lambda. Okay. And as for numbers, we have minus 3 here, plus 18, minus 6. How much it will be? It will be minus 3 plus 18 will be 15. 15 minus 6 will be minus 9. Okay. And so the most crucial moment comes now. Look at this. You might be tempted, nevertheless, to do this multiplication. Don't do this. It's not a wise approach. It will be very time-consuming. Let's better look at these two guys. If you pull out common factor 9, you will have 1 minus lambda, and this coincides with this guy. So we are on the right track. Look at this. Maybe we are lucky, maybe we are very clever, I don't know, but nevertheless, the situation is very nice. So let's pull out 9, 1 minus lambda. And after that, you can view this expression like consisting of two terms. So this is the first term, our horrible long term, and this is our second term. And they do have a common factor. They have this expression 1 minus lambda, which can be pulled out. And now I'm writing these brackets, my favorite brackets again. So 5 minus lambda, 1 minus lambda is what's left of the first term after pulling out, and plus 9. And it was all equal to 0. So look at this. This is the preferable way of solving cubic equations because it's much quicker and much more beautiful. Because you can still do all the multiplication, but you will end up having typical cubic equation. You will have to apply this algorithm, which I described in one of my tutorials, supplemental tutorials, which was titled even cubic equations. But it's maybe it's better to avoid this actually because it's a little bit longer, I'm afraid. Maybe unless if you're very experienced in this, if you don't have problems finding these cubic equations roots, then maybe it's okay. But nevertheless, I myself prefer to use that method. Okay, so what do we have here? So this term times this term in brackets is equal to 0. It can be true only in two cases. If the first term is equal to 0, which means that lambda is equal to 1, lambda 1, and when the second term is equal to 0. So 5 minus lambda, 1 minus lambda plus 9 is equal to 0. Okay. So what next? No, of course, we need to do multiplication here. Lambda squared minus, I think, lambda minus 6 lambda. I'm not sure. No, I make a mistake. Minus 5. Something is wrong. I know what's wrong. Look at this. I made a careless mistake. I pulled out this common factor from here. This is why I left with this one. And look at this. I forgot to write a minus here. So it's minus 1 minus lambda. So this instead of this. Okay. So, but now it looks a little bit messy and dirty. Okay, maybe it's better to rewrite it. 5 minus lambda minus 1 minus lambda. So I forgot to rewrite this minus last time. Okay, now I can do this multiplication. It will be lambda squared minus lambda. It will be minus 4 lambda. This will be minus 5 plus 9 will be 4. So we do have quadratic equation. And of course, you can use formulas, special formulas with discriminant and everything. But you know what? It's a better idea to have a closer look at this expression and realize that this is just a perfect square. It could be rewritten as lambda minus 2 squared. Much better, of course. As usual, it's much better to see all these tricks. And what do we need? And what do we have? We have lambda is equal to 2. Look at this. This is strange situation because we are definitely dealing with matrix 3 by 3, and we expect to have 3 lambdas because the cubic equation can have three roots, but somehow we have only two roots. This is the error already or what? You know what? Mathematicians prefer to say that we do have 3 roots nevertheless, but some of them coincide. So this situation is considered to be repeated roots. That is why we can call them lambda 2, 3 is equal to 2. You may ask me how can we determine which of these 2 roots, 1 or 2, are repeated roots, which are not. It's not necessary actually to realize this. I'm just saying it to you for illustrative purposes. But during test, during exam, you don't need to determine which of them is repeated, which of them is not repeated. It doesn't matter because the next step will be to find eigenvectors, and for this technique, for this algorithm, it doesn't matter. It works in both cases quite correctly. So you don't need to use these words, these strange words, repeated roots and whatever. You just all you need to do, you just don't need to get too surprised and maybe daunted if you end up having 2 or even 1 root instead of 3, expected 3. So that's it. So we have our lambdas now, and do you remember the objective of this tutorial is to learn how to find mistakes on the fly. So probably my lambdas are already incorrect. You notice that I already made attempt at making a mistake. Do you remember when I did these careless mistakes? Instead of writing minus 1 minus lambda, I wrote 1 minus lambda. So as you can see, no one can be guaranteed against mistakes. Or maybe there is a mistake still there, who knows. But don't stress out about it because we do have our wonderful techniques and how to check our results. Okay, so let's start. Now we need to find our eigenvectors. Let's start with lambda 1 is equal to 1. Let's discuss how to find eigenvector corresponding to this lambda. Just like in the previous example, just as like always, you need to get back to this matrix with lambdas, And now we need to rewrite this matrix, but instead of lambda, we can substitute our 1 current. So minus 1 will be minus 2 lambda. Or not lambda, but just minus 2. Minus 2, 3, minus 1. This is our first row. Okay, the second row, we are substituting 1, 5 minus 1. So minus 3, 4, minus 1. Minus 3, 4, minus 1. Is it correct? Yeah, correct. And finally, minus 3, 3. And here we have 1 minus 1. It will be 0. Okay. So this is how this matrix looks like. For the case of lambda is equal to 1. Of course, you need to multiply this by x1. x1 is 3. This is our eigenvector, and set it equal to 0, 0, 0. I'm doing it for the first time, but in the second step, when I'm going to deal with the second lambda, I'm going to omit this, because the more experienced you become in all these calculations, the more lazy you come. Actually, you just attempted to omit some of the writing. Okay, so now what I need to do, I need to rewrite this matrix and bring it to row echelon form. There's no option here but using Gaussian elimination. But you know what? I immediately disliked this matrix. You know why? Because there are two minuses sticking out here. It's just not comfortable situation. Can we get rid of these minuses? Too many of them. Of course, you know elementary operations. You can multiply each row by minus 1, and maybe things will look a little bit brighter. So 3 minus 4. It's not absolutely necessary to do it, of course. It's up to you, but nevertheless, I think it's a good idea. Okay, so what next? Next, you need to bring this matrix to row echelon form. But you know, the problem is that we don't have 1 here. Yeah, very frustrating. You always need 1 here, because 1 is a nice number. It allows you to get rid of these guys, to zero out them almost immediately. But we don't have 1, 2 here. What shall we do? In this particular case, for this particular task, of course, you can manipulate the third row. If you divide the third row by 3, you will immediately get 1 here, and then you can swap the third and the first row. But you know what? I decided to pretend that it didn't occur to me. And besides, there can be situations that there's no way of getting this 1 here. So let's discuss it, because it will be much more interesting to deal with this really difficult case. And you know what? I'm going even to give you even more techniques of how to deal with this situation when you don't have 1 here. Let's call it method 1, and I'm going to spend extra time on method 2 as well. So I hope it's going to be very informative for you. Okay, let's pretend that we didn't notice that we can get 1 here. What do you need to do in this situation? Nevertheless, you do need to get rid of these 2 elements to turn them into 0. The first approach, some people prefer to get 1 here by dividing the whole row by 2, but it's not my favorite method, actually. You know why? Because of course you get 2 here, but if you divide minus 3 by 2, you will end up having a fraction here and here, and it's very annoying to be dealing with factors, because they increase the risk of error considerably. No, it's better to avoid this situation. I prefer to use another technique. You know what I do? I multiply the first row by minus 3 and the second row at the same time by 2. Sounds like very fancy, but it's better than to deal with fractions. Look at this. If you multiply the first row by minus 3, the first element turns into minus 6. And the second element turns into plus 6. And if you add them together, you will have 0 here. Of course, it means that, as usual, as before, we are rewriting the first row, 2 minus 3, 1, and let's do this operation. So minus 6 plus 6 will be 0, as we discussed before, but be careful with the remaining elements. So this guy will turn into 9. 9 minus 8 will be 1, and the last element, minus 3 plus 2, will be minus 1. Okay, no problem, actually. And the same technique, the same idea could be applied for getting rid of this element 3. But this time you'll need to multiply the third row by 3, of course. And again, you will have the same situation. Minus 6 plus 6 will be 0. So here you have 9. 9 minus 6 will be 3. And minus 3 plus 0 will be minus 3. So as you can see, even though it sounds a little bit more sophisticated than before, but it's not a problem for you. You're university students, after all. You are not, first grade students, school students or something. you can deal with these numbers, I think. I'm absolutely sure. So we performed our first step. We did get zeros here. And the second step of Gaussian elimination is to get rid of this guy. And it's allowed to use only the second row. But of course, it's super easy. You can multiply the second row by -3 this time, and you will achieve your goal. So it means that we can rewrite to the first row and the second row. And let's see what happens to the third row. So it will be -3 plus 3 will be 0 here. And here we have +3 minus 3, which will be 0 again. So we did achieve our goal. This is row echelon form of the matrix. You know that row echelon form means that you have the triangle for zeros here. But you know what? Along the way, also we got a 0 row, and this is a very good sign. If you did get at least 1 0 row, it means that your lambda is absolutely correct, and your transformations, multiplications are correct as well. So this is a very good news. Okay, just like in the case for 2 by 2. In the case for 2 by 2, the indication that you are on the right track was that the rows should be proportional. But in this case, you can't see that rows are proportional because too many rows, 3 rows, too many numbers, and that is why it's better to bring it to row echelon form, and after that, just to look at the 0 rows. So if there are 0 rows, you are probably on the right track. Okay, so this is the first checkpoint for you. And conversely, if you don't have 0 rows, you should be aware that you made a mistake. Definitely, not probably, but definitely you made a mistake. Just get back and try to find your mistake somewhere. Maybe it was wrong lambda, just wrong lambda. Maybe you did some transformations incorrectly. So there could be many types of mistakes. Okay, now we need to push on. We need to find eigenvectors. What was the technique? First of all, you need to find leading elements for each row. So this is the leading element, this seed. Then you look at the columns of the matrix. You need to find the column or columns without leading elements. This is the last column. And this last column corresponds to which variable? X3. So this is X1, this is X2, this is X3. It means that our variable X3 is the free variable, and our convention is to denote it as parameter T. So it's parameter T. Okay. After that, you are ready to get back to the system of linear equations. Every row can be written as an equation. So the first row represents equation 2x1 minus 3x2 plus x3 is equal to 0. And the second equation will be x2 minus x3 is equal to 0. And now we need to solve this equation, and it's going to be our eigenvector. But in the first case, we need to use our x3. We need to substitute to each equation. And maybe let's do 2 actions at the same time. I'm substituting t instead of x3. And also I move t to the right hand side. So the second equation will be x2 is equal to x3, which is t. And the first equation, 2x1 minus 3x2 is equal to minus t. So it's much more convenient to solve it now. So as you can see, we already obtained our second variable. And to calculate x1, maybe it's better to express x1 first from this first equation. Minus t. It will be 3t minus t, it will be 2t. So it means that 2x1 is equal to t, which means that x1 is equal to t as well. So all our 3 variables have the same value, t. Okay, now it's time to write the solution of our system. The solution of the system is better to write it as capital X. And this is the column of our variables, x1, x2, and x3. And now we remember that these were t. Then it's better to pull out our t. And this column is our vector e1. So our vector e1, we can rewrite it, is 1, 1, 1, and put a frame around it. So this is our first result. But remember, we could have made a mistake quite easily. So it's better to do the check-in. Of course, the check-in will take you maybe half a minute, maybe, I don't know, maybe 15 seconds for some, but it's definitely worth it. It's absolutely worth it. So let's recall what was the check-in technique. A times our eigenvector should be lambda 1 times our eigenvector. Don't ever neglect this checking. It might be crucial for you actually. Okay, so with our matrix A, where matrix A, matrix A is here. 1, -1, 3, -1, -3, 5, -1, -3, 3, 1. And it should be multiplied by our vector 1, 1, 1. Let's do it. I never neglect this technique, this great opportunity to check yourself. This, just think about it. It's a great opportunity. Okay, the first row times this column. -1 plus 3 will be 2. 2 minus 1 will be 1. Okay. The second row. -3 plus 5, 2. 2 minus 1 will be 1. The last row. -3 plus 3, 0. 0 plus 1, 1. As you can see, this is the left hand side, and the right hand side should be 1 times e1, which is the same vector. So it means a great result. It means that we haven't committed any mistakes. Our vector is absolutely correct, and corresponding lambda is correct as well. So they both work together. So it's an excellent news. But you know what? Before switching to the next lambda, I promise you to discuss the second technique as to how to deal with these not very comfortable matrices. Do you remember when we wrote down the matrix for this lambda is equal to 1? We were dealing with quite uncomfortable situation. We didn't have one here, and that is why I showed you this technique of how can you achieve this row echelon form without having one here. Now I'm going to stop here before switching to the next lambda and give you yet another technique because it's really interesting. Maybe some of you would really like it. So method two of bringing the matrix to row echelon form. Let me copy this matrix here again. It will be 2 minus 3, 1, 3 minus 4, 1, 3 minus 3, 0. So what is the second technique? Again, we are pretending we didn't notice that we could have actually obtained one here. So what can you do? Maybe some of you noticed immediately that, of course, these numbers are not very good, but these numbers in this particular column are so wonderful. And it's a pity that this guy is the third column, not the first one. But you know what? It turns out that it's actually allowed to do the same transformations to columns as we did to the rows. Before that, when I was telling you about this Gaussian elimination method during our first tutorial at the very beginning of the semester, I strongly recommended you not to do anything to the columns because you were not very experienced in these calculations, and you could have easily made many more extra mistakes. That is why I recommended you to avoid doing this. But now you've grown quite mature when it comes to eigenvalues and eigenvectors. It's time for you to know the truth. Another trick is, it turns out that it is allowed to swap columns when it's absolutely necessary. So let's do it. Let's swap the first and the second column and discuss what it can lead us to. So I'm swapping the third and the first column. You know what it means? It means that the role of columns is swapped as well. You remember that traditionally the first column represents the first variable x1, this is x2, and this is x3. And if you swap the column, it obviously means that the first column here represents x3 rather than x1, and vice versa. And this guy remains at the place. So the reason why I didn't recommend you to do it, because the students usually get carried away maybe with the result, and they completely forget about this change of variables, and they end up having a wrong solution. But now it's time for you to know the truth. So as you can see, we have quite an excellent matrix now here with 2 1s here. So it will be a piece of cake. It seems like it's going to be a piece of cake to bring it to row echelon form. So let's start doing. So we are rewriting the first row, 1 minus 3, 2. And as for the second row, it's super easy. We can multiply the first row by -1 as usually and add it to the second row. So we have 0 here. 3 minus 4 will be -1. This will be -2 plus 3 will be 1. And I'm just, instead of rewriting the last row, maybe it's better to divide it by 3. 1, 0, 0. Something is wrong here. It's very good thing actually. Okay, so let's push further on. 1 minus 3, 2. Maybe as for this row, it's better to swap, maybe to multiply it by minus 1 actually, because it's better to have 1 here instead of minus 1. But you know what happened? Look at this. Then I need to perform the second step of Gaussian elimination to get rid of this guy. And I'm allowed to use the second row. So minus 1 plus 1 will be 0. And 1 plus 1 will be 2, by the way. Look at this, what happened. I did make a mistake. You can see this the resulting matrix, row echelon factory, doesn't contain any 0 rows. It means that I did a mistake. Where could I have made mistake? I think that is we are doing this for the second time, you know. I think that I did mistake somewhere here, careless mistake here. Let's try and check it in the first place. So we should get at least 1 0 row here. Otherwise, it would be absolutely incorrect. So let me find, let me check. Maybe my matrix A is not matrix A, but matrix corresponding to this lambda. Where was it? I have so many pages here. So let me check. If I copied it correctly, 2 minus 3, 1, 3 minus 4, 1. No, I copied it correctly. So maybe when I swapped the columns, 1, 1, 1, 1, 1, 0, 2, 3, 3, 1, 3. I found a mistake immediately. Look at this. It was just rewriting. This element was minus 3, and somehow I put 3 here. So I was lucky. I managed to find my mistake immediately. Okay, so now I can correct it. So it will be minus 1, of course, because do you remember I divide this row by 3, minus 1. And in this case, of course, we will end up having this 0. Okay, and so that's how you can. Sorry, it's too early. Let's pretend that we are doing for the first time. So by method 2. So what do we need to do next? We need to find leading elements, this one and this one, and the third row will correspond to the free variable. But remember, this was x3, this was x2, x1. So the free variable is x1, not x3, as you might be tempted to write. So x1 is equal to t. Don't forget about it. So that's why most of the teachers don't recommend to swap the columns, because many people have the tendency just to forget about this swapping, you know, by the end of the task. So after that, you can get back to your system of linear equations. So this is the first equation, and this is the second equation. Look at this. I'm making a mistake. I myself make a mistake. Do you know what kind of mistake I did? I forgot to swap the variables again. So the first one is represented by x3, and this is x1. So you now able to see how difficult it is. Just subconsciously, you tempted to write them in the usual order. But this time it's x1. It should be written here. Okay, now I'm going to substitute my x1, which is t, and x1 minus t. And you know what? I'm going to finish this transformation anyway, because there will be one more interesting moment popping up, which I want to discuss with you. Okay, let's finish this task, even though maybe it's not very interesting to you, because we already found this eigenvector first by the previous method, but nevertheless, it's going to be very interesting here. Okay, so from the second equation, we already know x2 equal to t, of course. And now to calculate the x3, maybe it's better to express x3 in terms of the remaining variables first, and then to substitute our x2, which is t, minus 2t. It will be just t. Nothing interesting here. It's a pity. Maybe I made another mistake here. No, it's not a mistake. So our vector will be x1, x2, x3, and again it will be t, which corresponds to t times 1, 1, 1. So we already obtained the same vector. So I spent some extra time on this first lambda, because I wanted to discuss two different techniques, two more maybe new techniques for you, how to calculate these eigenvectors in most effective way. Okay, but this is not the end of the story, as you know, because now we need to calculate the second eigenvector corresponding to lambda is equal to 2. You know, I recommend you to watch this tutorial to the very end, because this is going to be not quite typical situation. I remember discussing this situation before, but it was long ago. Maybe it was in tutorial 1, somewhere that. So be careful to watch this tutorial to the very end. Okay, so what do we need to do to calculate this eigenvector? The same procedure, of course. Let's get back to this matrix to remember this yellow matrix with lambdas. We need to substitute lambda with 2. So it will be -1 minus 2 will be -3. -3, 3 minus 1. This is going to be my first row. Okay, 2 here. -3, 3 minus 1. -3, 3 minus 1. And the last row is the same. Look at this. Very strange situation. But nothing strange. It's quite typical, by the way. Okay, so let's start dealing with this matrix. You know what? Even though maybe after discussing the previous exam, maybe you will be tempted to swap their columns again, but just wait a little bit. You know what annoys me, what really annoys me, that I have too many minuses sticking out here. That is why I prefer to multiply every row by -1. I just feel more comfortable when there are so many minuses. 3 minus 3, 1, 3 minus 3, 1. Looks much nicer in my view, of course. Maybe it doesn't bother you so much, but I prefer to have as few minuses as possible. Okay, so nevertheless, even though we don't have a 1 here, but we don't need it, because we can easily get rid of these guys during the first step by means of the first row. So we are just writing the first row. And how exactly are we going to get rid of them? Very easily. We can just multiply the first row by -1 and add it to the second row. And as a result, we get zeros here. The same here. Look at this. But you know what? This is a very good sign. Do you remember you need to have at least 2 0 rows? In this case, we have even 2 0 rows. Oh, what did I say? You have you need to have at least 1 0 row. But in this particular case, we even have 2 0 rows. So this is a real indication that we are on the right track. Okay, so what next? Next, we need to find leading elements. We have only one of them, leading elements. And these columns don't have leading elements. That is why variables x2 and x3 are free variables in this case. A very interesting situation. So it means that we need to denote x2 as the first parameter, t1, and the second x3 will be denoted as 2t. So in this case, we have just 2 free variables. Okay, and then after that, we usually get back to our equations. We are left with only one equation here. 3x1 minus 3x2 plus x3 is equal to 0. We can substitute our t's. Minus 3t1 plus 2t is equal to 0. And now we need to express x1 in terms of the remaining variables. It will be 3t1 minus t2 divided by 3. And it's better to be written in this form. t1 minus 1/3 times t2. Looks much better. Okay, so this is our third variable. And it's time to write down the answer in the in the standard form. So the answer looks like capital X, which is column of 3 variables, x1, x2, and x3. This is all, but I'm not going to answer it. Okay. So let's substitute our results. So x1 is equal to t1, x2 is equal to this expression, t1. Oh, very sorry for this. Very sorry. And x3 is equal to t2. Okay, so this time our answer looks a little bit strange, but let's wait a little bit. We already encountered this expression before, and what we need now, we need to split this column into the sum of 2 columns. So t1 times some column of coefficients plus t2 times the second column of coefficients. So let's see what coefficients should be put here after t1. So in the first row, we have t1. It means that coefficient is 1. In the second row, coefficient is 1 again, and we can't see any t1 in the third row. It means that coefficient is 0. So it's as easy, as simple as this. As for t2, we don't have any t2 in the first row. It means the coefficient is just 0. In the second row is 1/3. And here we have coefficient 1. And you know what? These are our two eigenvectors, E2 and E3, these columns, which are without t's. So the second vector looks very nice. E2 is equal to 1, 1, 0. But as for the third vector, I don't quite like it. I don't quite like it that it has fractions. It's better to do without fractions. What can we do with eigenvectors? As you may remember, and you should remember, you're supposed to remember, eigenvector is not a unique vector. Different students can get different vectors. But the main thing, these vectors should be proportional to each other. So it means that you can easily multiply these components by some constant so that they all turn into integers. I think in our case we can multiply by either 3 or maybe -3, doesn't matter. Let's multiply by -3. So it will be 1, and here we have -3. So this eigenvector definitely looks much better than this one with fractions. So these are our answers, but remember, the main objective of this tutorial, of this recording, is to teach you how to check your results. Let's not be lazy. Let's just check both vectors. So to do this, we need to apply our definition of eigenvector. Matrix A times our lambda, our vector, should be equal to lambda times our vector. In our case, lambda is equal to 2 now, but we have two vectors. So let's check every single of them. So E2 is 1, 1, 0. Let's check this. We need to check the left-hand side. Let's take our matrix. Oh, I already lost our matrix A. I have so many pages here. I wonder, where's my matrix A? Oh, this is really funny. Yeah, it's here. I found it under the table on the floor. -1, 3, -1, -3, 5, -1, -3, 3, 1. So this is our matrix A, and we need to multiply by our vector 1, 0. So we are checking the left-hand side. Okay, let's do it. So -1 plus 3 will be 2 plus 0, 2. The first component is 2. Let's switch to the second row. So -3 plus 5 will be 2, and that's it. And here we have -3 plus 3 will be 0. So the left-hand side gave us this one. What is the right-hand side? 2 times our vector, 2 lambda, will give us the same vector. It means that this vector is absolutely correct, which is good news. Very nice. But let's do the same thing with the third vector. We shouldn't be lazy because we want to get the highest score, during the test. Let's pretend that we are doing test. We need to get this highest score. Okay. Again, we need to take the same matrix A. Here it is. -3, 3, 1. And we need to multiply it by 0, 1, -3. Let's check what happens. So 0 plus 3 will be 6. Something is wrong. Something is wrong already. I don't know. Was 0. Okay. It's a good. I didn't even need to pretend to model this wrong situation. I even already did a mistake. So let's see what happens. Okay. So 5 plus 3 will be 8. Okay. Here we have 3 minus 3, 0. So this is our left-hand side. What about the right-hand side? Right-hand side should give us the same. Look at this. This time, it's not equal to the right-hand side. Where's the problem? Very, very sad. What does it mean? It might mean one of the two things. The first thing, maybe we did a mistake just in our calculations. Here's our vector in question. E3 turned out to be not quite correct. What's the problem, I wonder? Okay, let's try and see. Maybe, assuming that this is correct, maybe I did mistake in multiplication. So I decided to multiply every component by -3. So this will definitely be 1, and this is -3. I don't know. It's not so easy to find the mistakes. So the only thing which we are absolutely sure of, that we do have a mistake. But what kind of mistake? What is the second eigenvector? I have no idea. It should be so maybe what else could go wrong? Very good situation, actually. I'm really happy that I did a mistake, because the whole purpose of this tutorial was to teach you how to find mistakes, and all of a sudden I did make this mistake. what I come from. So x3 was so let's go over our transformations application from the very beginning. So I had x2 is equal to t1, x3 is equal to t2, right? Right. I'm substituting them here, here. Everything seems quite, nice. I have no idea. But the annoying thing that I did make a mistake somewhere. Where is it? The problem is, where is it? 1, 1, 0, and here we have 0, 1, minus 3. And the fact remains that multiplication, maybe, you know what? Maybe I just copied matrix A in the wrong way. It could happen, of course. So where's my matrix A? Let me find it first. It's not easy to find it. Okay, so let's have a look at it. Minus 1, 3, minus 1, minus 3, 5. Yeah. Matrix A is correct. Matrix A is correct because it worked in the previous case. So what about here? What did I do wrong? It's funny. But definitely, you know what it means. It means that the the components of this vector are not correct. Everything is correct because these two vectors correspond to the same lambda is equal to 2. And the second vector, something is wrong about it. I don't know. Maybe in my transformations here, I'm absolutely sure. I found the mistake. Somehow, I already made this mistake. Look at this. I was rewriting the first row here, and look at this element. It was 3, and I rewrote it as minus 3. Okay, I'm happy that I found the mistake. So plus 3 here, plus 3 here, and it means it will be minus 3 here. So it will be minus t2, t1. Okay, I'm really happy that I found the mistake. Minus t1. Okay. This is strange again. It affected only the first vector, but not the second one. Maybe I made one more mistake. I don't know now. But it's actually very good that it's happening now. It's going on now because it's absolutely perfectly models the real situation during the exam. You are under time pressure. You can't find a mistake. You start panicking. No, no. It wasn't a mistake. Do you remember I didn't copy this first row. Oh, how frustrating. I just was multiplying every component by minus 1. Now I'm making new mistakes. Oh, too bad. Okay, too bad. It was correct actually. Okay, but that's what happens to people all the time. So what was my mistake? I'm really frustrated. So it was all correct actually. T1 minus, I have no idea, to be honest. I have no idea. But we had definitely mistake here. How frustrating. So it's still plus 1 because our checking showed us that the first vector is correct, but something is wrong with the second one. I don't know. I can't find it. Just what happened to me? I don't know. Complete disaster. Oh no, I need to look at the solution. I do the solution first before this tutorial. Now I can't find it. Let me wait a little bit. That's my correct answers. So lambda is equal to 2. Where is it? So you know what? It should be vector minus 1, 0, 3. For some reason, minus 1, 0, 3. Why is it? So vector minus 1, 0, 3 should be this vector. So the first component should be minus 1 instead of the second. I don't know how could it happen. No idea. I made a mess here actually. Okay. So let me have a look at this first. So 3x1 minus 3x2 plus x3. I was ready to finish this tutorial and now I got stuck myself. T1 minus 1 over 3 to 2. I don't know. X1. I know. Such a stupid mistake. But it's actually all for the better. I didn't even need to imitate mistakes. It happened in a natural way. Due to my carelessness, I made a mistake and it was super difficult to find it. But I actually managed to find it. You know what I did? I just was in a rush and I wrote down the answer in the wrong way. Look at this. Let me take a blank page again. So you know what I did? I should have written this expression instead of x1, which I found earlier. And I wrote like x2 instead of this. That's it. Very stupid mistake, but all mistakes are stupid actually. So this should be x1, and x2 was denoted by t1, and x3 was denoted by t2. Oh, I'm really happy that I found this mistake. That's exactly what can happen to anyone during the test, especially. And now I'm doing this tutorial. I'm a little bit stressed out as well, just like you did during the test. So it's quite a natural situation. So I didn't even have to pretend to be doing mistakes. I was doing them actually. So now we split this answer into two columns. So it will be 1, 1, 0 again. And in this case, T2 will be minus 1/3, 0, 1. So this is our vector E2, and we already checked this, the correctness of this vector. But as for vector E3, it should be different. This is different this time. But again, just like in the previous case, I think it's better to get rid of this fraction by just multiplying all the components by either 3 or minus 3. I prefer minus 3 because I like 1 here. So it will be 1, 0, minus 3. So it looks like this is a correct vector, but nevertheless, I'm very stubborn. I want to check it anyway. Who knows? Maybe I made another mistake. Sometimes it happens. So what I need to do, I need to multiply my matrix A by E3 and check if this coincides with lambda E3, which is 2E3. Let's check it. Let's check it. It's better to do it because we want to get the highest score possible during our test. Okay. I lost my matrix A again. So A is minus 1, 3, minus 1, minus 3, 5, minus 1, minus 3, 3, 1. Times our vector E3. So we now have a new version of vector E3, 1, 0, minus 3. And let's do multiplication now. So it will be minus 1 plus 3 will be 2. Minus 3 plus 3 will be 0. And in this case, it will be minus 3. Minus 3 will be minus 6. So this is our first left-hand side. What about 2E3? 2E3 will be 2 times this vector E3. And it will be 2, 0, minus 6. Now I'm quite happy. Everything works perfectly. As you can see, everything is correct, absolutely correct. Of course, I did spend some extra time, but now, as you can see, everyone is prone to making careless mistakes. I did at least 2 careless mistakes during this tutorial. So you can see that, but I managed to correct these mistakes. Why did I manage to do this? Because I know these tricks, how to catch your errors on the fly. But you know what? We are not quite finished with this task. We are already close, but not finished. Because the assignment was to write down spectral and model matrices. Let's do it. Let's do it because it's very interesting in this case. So spectral matrix, lambda, is a matrix whose diagonal elements are our lambdas. So lambda 1, 0, 0, 0, lambda 2, and 0, 0, lambda 3. In our case, we had lambda is equal to 1 and lambda is equal to 2. So 2 turned out to the repeated value. You know why? Because it gave birth to two eigenvectors, as you see. That is why we use lambda only once, of course, like a first column. But in these columns, we write, 0 to 2 and 0, 0, 2, like this. So this is our spectral matrix. Okay, how should we write model matrices? Do you remember that for lambda is equal to 1, we had vector, eigenvector 1, 1, 1, this one. And that's how order matters. So this model and lambda spectral matrices, they are related to each other. You can't swap the columns, arbitrarily. So if your first column, like this, corresponds to lambda is equal 1, it means that here the first column should be vector corresponding to this column, only this order. But what about the rest, the remaining 2 columns? The remaining 2 columns contain lambda is equal to 2, and this vector 2 gave birth to 2 eigenvectors. You can write them here in any order. So the first vector was, I forgot about it. Maybe it was 1, 1, 0, if I remember correctly. And the second vector was 1, 0, minus 3, which gave us most trouble. You know what? In this case, you can swap the order of these columns, for example, because they both correspond to the same eigenvalue too. So this was indeed a very interesting situation, very interesting task, because what was unusual about it that we had only 2 eigenvalues instead of 3. And in this case, one of these eigenvalues may is supposed to lead to 2 eigenvectors. So that's it for this tutorial, and I hope hopefully it was very helpful for you for the future, because you probably realized watching this tutorial that it's always good to have some supporting techniques, some means of checking your results on the fly, because during tests and exams it's especially crucial, because you are pressed for time, and at the same time you want to get the highest possible score for every question, and if, even and you want some technique, some some method of being able to detect your errors on the fly and immediately correct them. So that's how that's what you did. That's what I did during this tutorial. So that's it. This is the end of this tutorial. Thanks for watching.